Welcome to module 10.2. We are in the Jack compiler. We are discussing the backend here, and in this particular module we will tell you the intricacies of handling the variables which are part of this Jack compilation. So, what is it that the compiler has to do when it encounters a variable? And as I mentioned to you, there are variables are of 4 types. It can be the class variables, namely field and static, and it can also be the for every subroutine you have variables which can be arguments and local parameter argument and local variables. So, how are we to handle these variables, and that is what we will quickly look at in module 10.2. So, though this is specific to Jack, this is the way even in a very high complex programming language like C, C++, C#, etc. This is how these variables are going to be handled. So, this gives you a broad introduction to how compilers in general handle variables, and specifically we will be educating you through the example of the Jack programming language. So, we will now start with so I am using the slides from the website chapter 11. So, what are the variables? Now, you see that we have a class named foo, and there are 3 field variables ABC, there are 2 static variables x and y. We explained in the previous module what is the difference between a field variable and a static variable. Now, there is some method. In this there are 2 variables a1 and a2 which are basically arguments. There are v1, v2 and v3 which are local variables. Now, look at one expression there. Let c equal to a2 plus x minus v3. Like, this is very interesting. C is a field variable, a2 is an argument, x is a static variable, v3 is a local variable. So, that statement c equal to a2 plus x minus v3 involves all type of variables that are present in the Jack language, right. Now, so when we are compiling, these variables should be stored somewhere so that we access it, right. So, what will happen here is when foo as a class is created, there will be a location, there will be 3 locations allocated for foo, the field variables of foo, namely a, b and c. And in the static memory, so if you look at the memory map, location 16 to 255 are to be allocated for static variables. So, this x and y will be mapped onto some part of that static. So, when you are compiling, you now fix that a, b and c are going to be allocated some memory, and the starting address of this a, b, c, when you are inside class, right, there is something called the this pointer. The this pointer will point to where the variables of that class are stored. So, when you are compiling the code, you ensure that whenever I am executing something related to a class, right, something related to an object, right, object of a class. Now, that object would have been created. For that object, for all the field variables, we will have some locations created, and those field variables will be in some consecutive locations, right, and the starting address of where that object is stored is that starting address is in the this segment, right. There is a this that segment that we have seen. The this segment actually stores the starting address of where the values of the variables are stored in the memory for the current object. So, keeping that in mind, similarly the argument will tell you when I am executing method bar, as you see here, the argument a1 will be stored, there is a segment, argument segment we have already seen, a1 will be stored in the 0th location, a2 will be stored in the 1st location, and there is a local segment in which v1 will be stored in the 0, 1 and 2. Now, this will point to some memory location, say 1000. In 1000 A will be stored, 1001 B will be stored, 1002 C will be stored. Now, given this type of an input, and similarly static without lots of generality, let us say 0 x is stored, 1 y is stored. Now with that, let us see what we need to do here. So I want to do C equal to A2 plus V minus x3. So now we go into our expression evaluation. In the virtual machine, which is a stack based virtual machine, I hope you remember the virtual machine that you have done. What we do, we push A2, push x, push V3, sub. When I do this sub, V3 gets x gets subtracted by V3, so x minus V3 is computed, and that will be on the top of the stack. So what will be in the stack? A2 and x minus V3 will be on top of the stack. Now I say add. When we say add, x minus V3 gets added to A2. So we get now, and what will be on top of the stack after add? A2 plus x minus V3. Now pop C. So A2 plus x minus V3 gets popped down to C. So this is how C equal to A2 plus x minus V3 is basically executed. Now this needs to get substituted. So when the program is executing, where will be A2? A2 will be in the argument segment and at location 1. Argument section, location 0 is A1, location 1 is A2, right. So A2 will be push argument 1, push A2 is equivalent to push argument 1. Push x is equivalent to push static 0. Without loss of generality, we assume that x is stored at 0, push static 0. X can be stored anywhere, and that index will be known. And then push V3, V3 is a local variable. So in the local segment, V1 is 0, V2 is stored at 1, V3 is stored at 2. So push local 2. Then sub and add are like this. And C is a field variable, and where will C be stored? That this segment will point to a address. From that address, that second location, 0th address there, if this is pointing to say 2500, 2500 A will be stored, 2501 B will be stored, 2502 C will be stored. So pop this 2, right. So this essential statement, this VM code, this is the actual high level Jack code that gets changed into this VM code pseudo level, but finally this is the VM code. So somehow we have to now translate this C equal to A2 plus x minus V3 onto this code, the last one here. And for doing that, this mapping of A2 to argument 1, x to static 0, V3 to local 2, C to this 2, this mapping needs to be present, right, and that is something which is very, very important. So the challenge in handling variables is to actually see how to arrive at this mapping between what is given as a code here and what is finally decided from that. So what we will be discussing in the next few minutes here, how are we going to do this mapping. So let us see how are we going to do. This is going to be very straightforward, right. So when I look at a variable, as such I have explained you in the previous module 10.1 itself, every variable has a name. Let us say x has a name which is x, then there is a type associated with it. In this case it is int, but there are in general in the Jack language we could have int, we could have char, we could have boolean, or it can be another class name also. For example, if you take other, the type associated with this is a point, right. So it's a class name also. So int, char, boolean and identifier, if you look at the grammar, these are all the different type, right. Now kind, for example, I already told you there are 4 kinds. So field, for example, x, its kind is field, point count, its kind is static. Other, if you look at this other, its kind is argument, right. And dy, if you ask, its kind is local. So I have field, static, local, argument. And then index, where is it stored in that particular segment, in argument segment 0, 1, 2. So I need an index. And of course there is a scope. All the field variables have within that class, and all the subroutine variables has local and argument within that particular subroutine, right. And the static variable of course has across all instantiations of the class. So these are the things, and this is at least what we do is we create something called a symbol table, wherein every variable that you are encountering when you are basically doing this compilation of a class, right, we actually create a symbol table. We create two symbol tables, one for this class, another for the subroutine. Right? The symbol table why we need to do this distinguishing thing is that the symbol table for a method is existing only when I am compiling that method, but the symbol table I am doing for the class exists while I am compiling all the methods. So, I need to have one when I am compiling. So, every Jack file will have one class, and while compiling that class I create one symbol table for the class variables, and that will exist till that entire compilation is over. And for every subroutine that we are encountering, we will create a symbol table for the subroutine, for exclusively for each subroutine, and that subroutine symbol table will go off as soon as we finish compiling that subroutine. So, every fresh subroutine I encounter, whether it is method, whether it is constructor, whether it is function, every subroutine I encounter, I basically create a subroutine symbol table for each one of them. Right. So, this is how we go about. So, this is a symbol table. So, I see x, y point count. So, what we do here is we are now creating this symbol table. So, this is the class symbol table that you see on the top, and this is the the subroutine symbol table for distance alone, like, and for every subroutine I will create and destroy it once I finish. So, what is there in the class subroutine? The class subroutine, see, note that there are three variables x, y, point count. All their types are int, right? All the types are int as you see here, and then the kind, x and y are of type of kind field, while point count is of kind static. And then x and y are going to be in 0 and 1, and point count in the this segment, they are going to be in 0, 1 in the this segment, while point count is going to be in the static segment. Here we have assumed without loss of generality it is 0. But what will happen in practice is, when we are compiling an application, it will have several class files. So, let us say class file 1, class file 2, class file 3, class file 4. So, we will compile in some sequence, it can be in any sequence, but when I am compiling class file 1, there I will encounter some static variable. So, we will allocate, say, there are 3 static variables. So, 0, 1, 2 will be allocated there. So, when we are compiling the next class file, we start from where we left in the previous. So, there needs to be some sort of a communication between one class file and another class file in terms of where I am going to store the static variables, right. So, there is a class file called bat, just say there are 2 classes called bat and ball, right. So, the bat has some 3 static variables that will be allocated 0, 1, 2. When I am compiling ball, when I find another static variable, then I should allocate 3 for it, right. So, in long sense, when you start looking at compiler, you will be studying something called linking. Linking is nothing but trying to establish some communications between different files which eventually make one executable, right. You would have worked on .c files, right. There will be several .c files, right, which will eventually make one executable. For example, even in your hello world, there is some stdio.h file, right. You are using printf as a function, you do not know what printf is, right. So, you just use it, and who knows what printf is? The stdio.h file actually knows printf. So, when you are compiling, you take your hello world code, and the compiler also takes the stdio code where the printf routine is there and links it, right. There is a linking that is happening. So, what are the different aspects of linking? Linking is trying to link several executables together, right, several files together. So, this is one very simple example of linking, right. So, that you can keep in mind. So, here without lot of generality, we have said that point count is 0, but in principle the point count can be 3 or 4 depending on how many other class files or Jack files you have compiled for this particular application before compiling this particular file, right. Now, coming to the next one, now we are talking of point. When we are compiling this method, so there is one argument which is other, it is of type point, right? This is a type is a class here, and the name of that is name of the variable is other, and it is at 1. Similarly, dx and dy are local variables, dx, dy int, they are of kind local and they are in 0, 1. Now, what is this, right? Already I told you that whenever a method is executing, there is a need for accessing the field variables, like what we have seen in this case, right? There is a need for accessing a field variable. In this case, I am accessing C. So, that means as a method, I need to know where that variable C is stored. So, I need to know where that this is basically stored. Okay. So, that is why whenever we are calling a particular method, we also pass the reference, that is where that particular object is stored, that this will point to where x and y are stored. This is a, we have already seen this is a particular 16-bit variable. Now, in this I store 1500, that means x is stored at 1500, y is stored at 1501. So, but I need to know where this is when I am compiling. So, by default, whenever I call a method, this is stored as argument 0, and everything else will be stored from 1, 2, 3. So, here it has only one argument. So, it has 2 or 3 arguments, then it will have argument 1, argument 2, argument 3 like this. So, one of the things that we need to understand here is that we need the variable this as a part of your argument, because whenever this method is going to access a field variable of that instantiation of the object, it needs to know where that field variable is stored. Of course, static it will know, but it needs to know where the field variable is stored, right. So, this is very, very important. So this is keep this in mind when we are constructing the symbol tables, right. Now that we have constructed the symbol table, right, now it is very easy for us to now go and start it's very easy for us to go and start compiling these codes, right. So, to just sum up, one class level symbol table is created, which is a top one as you see here, and then that is used for the entire, when you start compiling from this to the end of this class here. But then there is a symbol, there is another symbol table that is created here, which is for every method. So, when a method is entering, that symbol table comes into existence. When the method is completed, that symbol table is erased, right. So, we will have something called a current symbol table, and for subroutine, current subroutine symbol table, but we will have one class symbol table which will exist for the entire duration of the compilation of this particular class file or JAK file. Okay. Now, right. Now, every time that you see, say let y equal to y plus dy, this is a source code in this case. Now, immediately what we do, we push y, then push dy, and then add and pop it back to y. That is what we do, right. Y equal to y plus dy. How do you execute it on the stack based virtual machine? You first push y, this y, then push dy, then you add, right, push y, push dy, and then you add, then again you pop it to y back, right. Now, what is y? Y, immediately you go to this symbol table is created before you come here. So, that's class. So, before I start, let us say let y equal to dy is somewhere here after this. Okay. Now, by the time I start executing this, the class symbol table will be created, and for the current method, that symbol table will also be created, okay, for the current method, right. So now, so this will be available. So, the moment I see y, push y, where is y? I go back, it is field 1. Then I say push dy, dy is local 1, add, and pop y, y is again this one. So, by using this symbol table, I can translate this push y, push dy, add and pop y to push this one, push local 1, add and pop this one. So, this is the very simple things, right. So So this is very this basically we are now talking of the life cycle. The life cycle of a field variable is for the entire class, right? And so if it is a field variable, every object instantiation from the start to the end, this scope of this variable is there. When you are compiling the class from the start to the end, there's a life cycle of the field and static variables are there. The case of local variables and arguments, it is for within that particular method or constructor or function, right? So it is, so the life cycle is within that, right? Now, you know, in complex programming languages like C, right, you can declare variables anywhere. Here we have now restricted to declaring variables at the beginning of the class, and here also we are restricted to beginning within the subroutine. We have restricted to declaring all the variables at the beginning, right? But this variable declaration can happen anywhere inside, right? So I could have then within, so the scope, if you remember what you have done in C, the scope of a variable is within the block in which it is described. So for example, if I say for int I equal to 0, I less than something, only within that for loop that I will be, I declaration is valid. Outside it, it will not be valid. So, but so the moment I have this type of nested scoping, right, then that basically I will have multi levels of symbol table, and then we have to use that. In general, in a complex programming language, we will land up with these type of multi levels of symbol table. But in Jack we are not doing it. We are now restricting one symbol table for class and one current symbol table for the current subroutine that is being executed, right. So we will now proceed on to the next module, where we will be talking about how to handle expressions. I hope you understood this. I would like to see more postings coming on the website. We have seen some people are asking doubts, but there are not that many doubts that we anticipated. Hope either we are very clear, which we are happy, at least you post saying whatever you have taught is clear, right? We just want to ensure that you are with us in the course, right? We will now go on to module 10.3. Thank you.